Yeah, welcome back. We have been doing some exercises under this material balances. So in the first two examples, we were able to carry out some simple mass balance calculations. Now let me take up another problem which involves energy balances. Now as you can read from this problem statement, now ethyl benzene from this temperature and pressure is to be heated to this temperature and should be compressed to this pressure. Now you have two possible options. Option 1 is the liquid ethyl benzene is sent through a pump to increase the pressure to the desired value, followed by heating it to the required temperature. The second option is the liquid ethyl benzene is first vaporized at constant pressure to an intermediate temperature and then compressed to the required pressure. Which of these options do you recommend? So you are required to simulate both these options and try to compare their performance. And finally, you are required to suggest which one of these options are better and probably identify what are the reasons for choosing a particular option. Now let us try to simulate this problem. Now the only component that we are going to handle in this problem happen to be ethyl benzene. Say next. Now choose a property method. Say next. Go to simulation environment. Now as is required, we would like to simulate both the options in the same simulation. I'm going to use a duplicator block. You have already seen what is the use of this duplicator block. Now as per the first option, first of all, it is compressed to the required pressure. Sorry, it is pumped. The liquid ethyl benzene is pumped, thereby increasing the pressure from 14.7 psi to 73.48, followed by heating it to the required temperature. So I am going to use a simple heater because we are interested in calculating the energy balance, but not interested in actually going into the design aspects. Now, as you know, the heater model will not address what type of heat exchanger is being used, what are the design aspects, what type of heat transfer area is required, and so on. So as far as this problem is concerned, because we are dealing with only energy balance without going into the details of design, now this simplified model will do. Now in the second option, we are first vaporizing it by heating it to some intermediate temperature, followed by compressing it to the required pressure. Now let us connect the material streams. Now this is the ethyl benzene entering at the given conditions. Now this is, let us say, first option. Now similarly, any number of outputs from this duplicator will have the same information as that of the input. So let me rename this as option 1 and this as option 2. Now as you can see, for this entire problem, there is only one input stream which need to be specified along with the required information with respect to all the blocks. So having drawn the flow sheet, now we'll be in a position to go to the next input screen. Now you can see the information is required with respect to only the input stream plus the blocks. Now let me choose the unit system, change the unit system to English because we are using Fahrenheit and PSIA. The feed is entering at a temperature of 77 degrees Fahrenheit, a pressure of 14.7 psia. Let us calculate this per 100 lb moles per hour of ethyl benzene. We are required to compare the performance of these two options, right? So whatever is the flow rate, that doesn't really make much of a difference. So we have specified stream 1. Say next. Now this is with respect to block 1. As you are already aware, there is no mandatory requirement to specify the block with respect to a mixer. So we will be able to proceed. Now this is with respect to the pump. Now I know the discharge pressure for the pump should be 73.48. The inlet pressure is 14.7. Now the discharge pressure is 73.48, right? So the block B2 is specified. So go to the next input screen. Now this is with respect to block B3, which happened to be a heater. Now we wanted the outlet temperature from the heater to be at 752 degrees Fahrenheit at a constant pressure of 73.48. Now you have a number of options to declare here. If you say 0, that will be taken as 0 pressure drop. Any value less than 0 will be taken as the pressure drop. Any value given as a positive quantity will be taken as the operating pressure. So you can say here, instead of 73.48, 0. So we have specified block B3. Go to next. Now this is with respect to the heater available in the second option, B4, followed by the compressor. Now let us look at the heater. Now do we know the temperature? As far as the problem is concerned, the liquid ethyl benzene is vaporized at constant pressure to some intermediate temperature. Now we don't know what is the temperature to which it should be heated first. The idea here is when it is heated to some intermediate temperature at a constant pressure of 14.7, and ultimately when it is compressed to 73.48, there will be obviously some temperature increase. So this intermediate temperature should be chosen such that after compression, you should be able to get the required temperature of 752. Because to start with, we may not be having any idea about this intermediate temperature. Let us make an approximation with respect to the temperature. Let me assume the temperature as 500 degrees Fahrenheit, pressure 14.7 psia, constant pressure we are trying to heat. Say next. So we were able to specify even block B4. Now we are talking about compressor. The same model can be used to simulate either a compressor or a turbine. So now we are using it as a compressor. Now you choose one of these options, say isentropic. We wanted the discharge pressure to be at 73.48. Now you can see the required input is complete for the entire simulation. Now we'll be able to run the simulation. Yeah, all these blocks are calculated. So the results for we will be able to see the results. Now the question here is, because we have approximated this intermediate temperature as 500, now as you can see, the ethyl benzene must be heated to 752 degrees Fahrenheit, and also the pressure must be increased from 14.7 to 73.48. So in option 1, we were able to get the required temperature and pressure for the exit stream. Whereas in option 2, now what is going to be the temperature and pressure? Now as you can see, the pressure is all right at 73.48, but the temperature is only 583. So what happened? Now the inlet to this compressor is at 500 degrees centigrade because we have chosen the outlet temperature from the heater as 500, but the pressure is 14.7. So when you heated the, when you compressed from 14.7 to the required pressure of 73.48, there was a temperature increase of about 83 degrees Fahrenheit. Now we must be able to choose this temperature such that when you compress, ultimately you must be in a position to get about 752 degrees Fahrenheit in the exit. Now to do this, we can use some kind of a design spec to calculate that intermediate temperature. So go to flow sheeting options, design spec. Now what is our requirement? The outlet temperature. So that is going to be your define variable, out T. Now what kind of a variable is this? It's a stream variable. Now I am going to stream variable. Stream is option 2, the exit temperature from the option 2, stream. the variable is temperature. Once again, be careful about the units. So we are following only a consistent unit system, English unit system. Now we have defined the variable, that is the measured variable. Now what is our requirement? This outlet temperature should be at 752 degrees Fahrenheit. Let us say some tolerance of 0.1. Say next. Now what is the variable that you are trying to manipulate? Remember, we have chosen some intermediate temperature for the exit of the heater. So we need to manipulate the block variable, which has been approximated as 500, such that when it is compressed, we'll be able to get 752. Let me go back. Now the variable that I'm trying to vary happen to be block variable. Block is B4, that is the heater. Then the variable is temperature. Once again, you have in Fahrenheit. So 500 is, let us say, the lower to about 750. Now we have specified the design spec run. Before running, now you can see now what is happening in the design spec. We started with an approximation for the block variable, that is the outlet temperature of this heater as 500. Solve this heater model, then followed by compressor model. You will be able to know what is the outlet temperature for this stream. Now compare that with your requirement of 752. If it matches, fine. Otherwise, you may have to re-assume the temperature within this block until you are going to meet with your requirement. Now the measured variable is here, the manipulated variable is here. Now because this design spec is connecting both these units, now both these units will have to be iterated till convergence is reached with respect to this design spec. Now let us run this problem. Now you can see B4 and B5, because of the design spec, are iterated a number of times. How many? About 4 times. And the method that has been adopted here happened to be secant method. We were able to reach a convergent solution. Now we can once again look at the results. Now I am interested in obtaining 752 degrees Fahrenheit here. So we were able to get that required temperature, same as the pressure. And what variable, what value of the temperature gave me this result? What is the intermediate temperature? So you can see about 664.32 degrees Fahrenheit. Only when the outlet temperature from the heater is 664. So when you compress from 14.7 with an inlet temperature of about 664 degrees Fahrenheit, 14.7 to 73.48 compression will result in an increase of temperature from 664 to 752. In any way, we were able to get exactly the same requirements by both these options. Now, which of these two options you are going to prefer? How do we compare which one is going to be better? Now, the work requirements and the heat requirements are actually given here. Now you can see, because we are following English unit system, now if you want, you can look into the results. Now let me change. This is about 1.90348 kilowatts. That is the total energy required by the pump. Whereas the heat requirement, the energy required for the heater is about, let me change these units also into kilowatts, about 1460.59. 1460.59 plus about 1.9 is the total energy required by first option. Now in the same way, let us also evaluate something like 1460 plus 1.9, say 1462 roughly. Now you can also check up what is the total energy required by the second option. Again in kilowatts, about 1317.32 kilowatts of energy is required in the heater, followed by the energy required in this case in terms of kilowatts, network required 145. 145 plus 1317. Now you can see the total energy required by both these options is exactly one and the same. In fact, even without calculating, we know this result. We might have solved several problems in your thermodynamics. The initial state and the end states are exactly one and the same for both these options. Now, energy being a point function doesn't depend on the path of the process. So the total energy required is exactly one and the same for both these options. But even then, you are asked to choose which one of these options do you prefer and why. Now, in order to decide, I think you can go into the details and analyze what is the total energy required for both these options, though it is one and the same. Now, you can see that in the first option, you require more energy in the form of heat, whereas in the second option, you require more energy in the form of work. If you recollect, you require about 1.9 kilowatts of work, whereas in the second option, you require about 145 kilowatts of work. What do you mean by this work? Work is a superior form of energy compared to heat. So as a result of that, now you are required to supply this much of energy in the form of probably electricity for both pump and compressor. Now, how are you going to get your electricity? This being superior, you may have to convert some kind of heat energy into work, which will result in only 30% conversion. So it is always better to use or make use of a low level of energy like heat instead of work. So when compared between these two options, though the total energy required by both the options is exactly one and the same, most often you are required to choose only the first option because you will be using less amount of work, mechanical work, right? Which being a superior form of energy, you are now going to, the entropy increase by first option is going to be lesser compared to the second option. Now in this way, of course, you will be able to choose one of these options. Option 1 is supposed to be much better when compared to option 2. In fact, this conclusion can be drawn even without going into some kind of economic details. When you go into economic details, probably pump is going to be much cheaper compared to a compressor. And it is always better to handle increase in pressure when it is in the liquid phase. You know, liquids are going to be insensitive, liquid volumes are going to be insensitive to changes in pressure, whereas vapor volumes are very sensitive to changes in pressure. In this particular case, the compression is being handled. Increase in pressure from 14.7 to about 73.48 is being handled in the liquid phase, whereas in the second option, we are handling that compression in the vapor phase. So because of large volume change associated with vapors subjected to pressure change, now the energy required would be obviously quite high compared to the energy required when you handle that compression in the form of a liquid. When compared between liquid compression and vapor compression, the work required in the case of vapors would be quite high. So as a result of that, option 1 is always a much superior option compared to option 2. Now, in the same way, you will be able to even handle energy balances irrespective of whatever may be the unit that you are having in a given process. Thank you.